All right, everyone, we'll wait a few minutes to get everybody on board. This is happening earlier than usual. Here we have 29 people. I'll wait a little more. All right, the number of people goes up and down. Can you just say something on the chat so that I have an idea how many we've actually got? Hey, cool. So we do have somebody. Well, Stefan, you've been here before. Well, I see 13, 24, then 13 again, then 27. I don't know what it means. Anyway, two on your account. Okay. All right. So then let's get to it. Hello. All right. So today we're going to do threads, and we have a lot of stuff to cover. Then we need to talk a little bit about the exam, and I will start though playing a little bit with whatever I put together to have some kind of proctoring during the exam. So until some more people show up, because this is much earlier than usual. Can you please go and you'll see what I'm doing. Uh, so just go to the class web page and then click on home, and then you'll get to what could pass as a website, but is not really. And then click on exam here. All right, so what happens when you click on exam is you're going to get to the page that we will be using to take our exams. This is going to help us watch how you are doing. So the first thing to look into is to make sure that in this area you see yourselves. Basically, this is my camera, but I covered it with pink post-its, so it looks like this, right? For that, you'll need to provide permissions from here to the camera. Then you will need, so you just follow these steps. Then you go to OBS Ninja, you click on it, and it tells you, I think the instructions will tell you here. Now, I just tell you to share the screen, so practically you click on this, then you click here, then you select your screen, you share, and then this will share the screen, and you have to take this URL as it is. and copy it here. Right, then what you would do, but you don't need to do it now, you would copy this registration request, paste it in whatever communication you have with your professor, and you'll get an email with an invitation string, and you'll also get a password. You decrypt them, and then that's how you connect to the exam server. Now, what if your laptop camera is not working? Well, I don't know what to do in this case. I will probably go ahead as it is, but try to get something working. Maybe borrow a camera from somebody who doesn't have the virus, though. All right. You don't have a webcam at all? Well, try to get one. If not, we'll figure out something. I will not leave you out of the exam just because you don't have a camera, but we'll have to figure out something. Well, but if your phone cam, I don't know how. Can you connect the phone cam to your laptop? I don't know. Well, I'll have to think of the solutions yet. But basically, here we would see you, and then you would put your PuTTY terminals here. So, and then as you would be sharing the screen with us over OBS, we would be seeing you and your work, and that's the best we can do, right? So, if you don't have a camera, maybe it's a good idea to announce us ahead of time, because when the event starts, it will be more stressful. Yeah, I don't know if you can work with the phone cam. I have no idea how you can connect it to the laptop, but maybe you can. Actually, I think I've done that once. Yeah, there is an application, let me see, that installs, I have an Android, so there is an application that installs something like a webcam server on it, and then you can connect to that from your browser. There is a way, but okay, the yellow section is, so you will get in email an invitation string, something that looks like this, right? You'll copy it here. Your professor will give you a decryption password, and then down here in this area, you will get connection details, meaning server IP, user, password, and whatever other instructions. Well, if you don't see yourself, so you should see yourself, right? For me, you don't see me, you see my cam cover here, right? But if on your laptop, you should see yourself. And if you don't, you should come here and give permissions to the browser to your camera. Yeah, that's not all right then. So try to figure out why you can't see yourself. Maybe use Chrome. I know Chrome works. I don't know about Firefox. Maybe Firefox does too. I I I I haven't really tried it. Let's see if Firefox does the trick. Yep, Firefox works too. So yeah, I don't know. I don't know why it wouldn't work for you. Opera works fine. Okay. Uh, yeah. Okay. This is a good point. You have to go HTTPS. If you just go HTTP, I believe it won't work. So you have to go to the secure version of the site. HTTPS should do it. Yes, this is what we're gonna use for our tests. I'll let you know how those happen, but I'll do that at the end of the class when there will be more people and more will hear it. For now, playing with this, we'll have a little more time later, but I prefer to start with it so that more people gather. When will be the test? I'll let you know at the end of the class. All right, guys, so let's get ready. We need to jump into threads today. So let's get started with. I'll just open two programs here, and I'll start talking, and then I'll get to them as well. All right. So we have started looking at ways of performing concurrent calculations to use the resources of the system, to use the many processors, many cores that we have. For that, we started with fork. So if we want to do concurrent calculations, we just create another process with fork. And then if we need to aggregate those calculations, we somehow need to send the data from a process to another. And for that, we introduced pipes and FIFO. And lastly, just a little bit, shared memory. And that's relevant because threads do exclusively shared memory. So now, as we're moving to threads, the approach changes a little bit. It's going to be a little easier, but there are some differences. So what I put here up on the screen, and that's how I'm going to start, is on the left you have a program that creates 10 child processes, each of which prints out its PID, and that's it. And on the left you have an equivalent program that does the same thing with threads. So have a look at them, and I'll see what people ask here. Yeah, T-flag, I've changed the plan a little bit, so let's leave the test planning for later towards the end of the class, because I came up with a different scheduling. All right, so let's have a look at this code. You should be quite familiar with the one on the left. So we just have a 4 from 0 to 10, create a child process, print PID, exit, and then 10 waits to wait for the child processes to finish. Yes, Steph, yes. Threads work with a function, much easier. So when you create a child process, what you end up doing is actually duplicating the whole thing, but then separate the child specific code using this if. When you work with threads, the way to do it is write in a function the stuff that you want to be executed concurrently, and then run that function in a thread. So here is how it looks when we do it with functions. You have a function that prints out, well, the thread will not have a PID, it will have a pthread self. This will be the idea of the thread, right? It prints it out. And then you simply run this in a thread. Now, how do you do that? First of all, we will need to declare a handle for each thread. Okay, 10 threads will have to have 10 handles. For processes, we didn't need that. We could simply wait for whatever process finished first and do that 10 times. Here, though, the equivalent is to wait for each thread individually. If you want, this would be the equivalent to wait PID. We never used wait PID. We use wait because it's a little more comfortable, but this is the equivalent of wait PID. So we declare 10 handles so that we can wait for each one of them. And then we create the threads. Now, how do we create the threads? Simple. pthread create is the function that does that. And you pass it the handle where the handle for the thread should be stored. Then you pass this null. This null is where you would be passing attributes that would control certain aspects of the thread execution. But for now, we don't care for those. So we just go with the defaults. Then we pass the name of the function to be executed in this thread, in this case, f. This is actually a pointer to function. Pointer to functions are really easy to use. You simply put here the name of the function, no parentheses though, because that's a call to the function. This is not a call to the function, it's just its name. The declaration of pointers to functions is a little uglier, but using them is this much, nothing else. And this null is actually the argument that will be passed to the thread, this guy. But we don't pass anything for now, so we just put a null. So this is it. This is the whole thing. You just write the function, run it in a thread, and you're done. So maybe if you look at it, it's a little more code than in the case of processes, but I find it more, let's see, clearer, because whatever goes in a thread it's a function. No, f is not a handler. F is the function to be run by the thread. The handle of the thread is just a descriptor. It will be in TI. So if we are to compile this, so I'm going to compile the process stuff just so that we have it as a comparison to see how it works. And we run it. Right, this is what it does. It just prints out 10 PIDs. Yes, Steph, I'll get back to this in a second. Now, when we compile a threads program, we need to add something else. So look at this. If I try to compile this thread program as it is, as before, I will get an error. So here is the story with that error. Hold on. Now, this error is not actually a compilation error, it's a linking error. The code is correct, but we need to pass a library. You see, LD is the one that gives the error, not the compilation. You also notice here that you have this really ugly name that ends in .o. This is the object file, which is an intermediate file between compilation and link editing. So let's clarify how compiling actually works. Some of you may have seen this, some of you may have not. So you start with a source file, right? And then through compiling, you end up, although you don't see it with GCC, and you might see it in other cases just because you see the files on the disk, but nobody really bothers about. If it's all correct, you're not going to have trouble with this. You end up with the .o function, or in Windows you get it as .obj. All right, this is an intermediate compiling file which takes the source code and puts it in a structured way. Oh, so you've seen this. All right, so then through linking, you get the actual binary, or in Windows it would be an exe. So when I compiled, this passed fine. This is the one that failed. And you figure this out because you see here that the error is about an object file, and that LD, which is the linker, is the one complaining. And the problem is that it doesn't find implementations for this. So pthread.h is good enough to pass compilation, but we also need a library. So to add that library, all you need to do is to add here -pthread. And then it works. All right? And then we run it. And well, the pthread self returns much uglier numbers than the process PIDs. But basically, the two programs are equivalent. All right? Look, I'll just load them up again. So there was a question from Steph. Yes, a function that needs to be run in a thread must have the signature. It has to get a pointer and it has to return a pointer, right? That's a standard. And because of this, you can see that you can only pass one pointer to the function running a thread, and that function returns a pointer, which you could catch here in pthread join, but we don't care for it and we put a null. Just like for processes, we didn't care for the exit code and we put a 0. All right. Okay, you still don't get why pthread, why the include is not enough. That's because the header declares the functions like this and this, but does not include their implementation. Their implementation is in a library which is actually an archive of object files of .os or .objs. So when you compile your program to generate the OBJ, you have here everything you need, and you put in that OBJ a reference to pthread create and pthread join because you know about it from the header, but you don't have its implementation. So when you make the executable, you have to take the object file along with whatever libraries, which also bring object files. Libraries are just an archive of object files. And those together contain all the code that can lead to executable. Without -pthread, the thread-specific libraries are not included in the linking, and then you have no code to use for this, so it fails. Got it. Awesome. Now, pthread is the default threading library on Linux. It comes from POSIX threads. There are many other implementations of threads. Every language has its own way of doing it. This is the C way in Linux. In Windows, it's going to be different, but it's going to be different in terms of arguments and API, but the notions and the spirit of it is identical. So that's how we create threads. That's it. Now let's see how we pass parameters to threads. So I will load here 0.3, I believe it is. So we have here an example in which we pass a parameter to a function. If you recall, we were printing out an ID of the thread, right? The pthread self. Pthread self, let me open it really quickly. So pthread self is like a get PID, but not really. It's somewhat equivalent. But what I'm thinking is, what if why don't we print out this index of the thread, right? The index at which it was created. Yes, it works. With me, yeah, it should work. So I would like to pass to the thread this index I, right? So that's what I'm doing. But it's wrong. I just want to see you how it's wrong, and then I want you to get why it's wrong, and then we'll do it right. So I'm passing I'm passing its address, right? Because this requires a pointer, and then here I convert a to a pointer to int, and then I take its value and I print it out. Thank you, Berzent. You caught it. Let's compile it. Let's have everyone see this failing. So it's compiled, and now that we run it, look at this. If I run it again, all right, so now it's consistently wrong. In the previous class, it wasn't. So you can see that I have 4 printed twice. I played a lot with this, so I actually got. Hold on, I'll show it here. I don't wanna take the code off the screen. I played a lot with this, and I managed to get also this execution happening, right? Often it would be like this. Basically, each thread would print its own ID, but not necessarily in the order you would expect, right? Other times you'd get one printed twice, and other times it would all go to hell. So the problem here is, and Berzin got it right, is that we are actually passing the address of I to every single thread. Every single thread is looking at the same memory location and takes its content, but its content is changed by the main thread. So whenever the thread gets processor, it will read whatever is there, and it may be what it expects or not. This case actually happened when I had the threads do something else before the printf. So by the time they reached printf, the main function had reached this. So two of the threads caught I equals 0, and then the rest of them caught the incrementation of I to 2, and then they printed this. So this is the wrong way to send an argument to a thread. Okay, but what would be the good argument, the good way? So the good way would be one of them, there are many, would be to have a static array in which we put the value of I and then we pass to each thread a different value, right? A different address. Then things will not really fail because each thread would look in its own memory location and it will print out what we expect it to print out. And in this case, it actually, I think I have it compiled. In this case, they're quite nice and printed really in order, but look, sometimes it's not exactly in order. Sometimes it goes off. Are there questions here? All right, so before I go on with the parameters, I need to go back a little bit because I skipped a piece. You guys caught on to the issues, and I kind of skipped the big part. The big part is, okay, this is how you create a process, this is how you create a thread. Why would you use one versus the other? What's the good for one? What's the good for the other, right? So let's see a little bit how the process looks like in memory and then how threads go in there. So a process has the following very simplified structure in memory. It will have a context, right? And this context will contain its process ID, details about ownership, the open file table. There will be things specific to the process, not to the program. Then it will have the source code, right? Which are the instructions to be executed. Then there will be constants. Constants Steph, that's a good question. There will be no zombie threats, but I'll explain. I need to get through this, and then I can explain your question. So constants in a program are these things. This is a constant. This is a constant. Everything that's hard coded. Okay. Then you have variable. This will be the global variables. Then you get the heap, and then you get the stack. Heap is the location where you allocate memory dynamically with malloc, and stack is the place where you register the sequence of nested function calls, right? And it keeps going up and down. As you end the function, you move down in the stack one position. If you call a function, you move up. And depending on how you want to visualize it, heap grows downward and stack grows upward. I understand another way of visualizing it is that they are back to back, but in reality is just a big chunk of memory in which you allocate stuff dynamically or for the stack, and that's it. So this is what's in memory when you start the process. Now, of these pieces, two of them never change really. These two never change. And we'll call this the pure part. The lower ones are the impure, because this can change. So when you do a fork, what happens is you'll get another context, right? So this is, let's say, context F from the fork. But you will keep the same source code and the same constants. You don't need to duplicate this in the memory. However, you do duplicate the variables, and you do duplicate the heap, and you do duplicate the stack. So practically, when you create a process in memory, you duplicate a lot of memory. And this is the big piece. The heap is going to be large usually, right? But when you create a thread, and this is the main difference, when you create a thread, you keep the same context, you are actually in the same process. You keep the same source code. You keep the same constants. You keep the same variables. You keep the same heap. However, you keep the stack, but you allocate another stack just for this thread. Practically, you allocate a buffer in the heap and you give it to the thread to use it as stack. So, if fork creates another process and reuses only the pure things that don't change, a thread doesn't duplicate anything. It just allocates a buffer for its stack and then has access to the whole lot of memory of the process. You won't need to use pipes. You can use all the global variables and all the heap in a thread. It's literally like shared memory. You do need a separate stack though, because look, main, after it creates the functions, it keeps calling other functions. So main will have its own stack of function calls, right? Nested function calls. F, which is in the thread, will also need to have its own stack of function calls because this one calls another function. So you need a stack, a separate stack for each thread. But then that's it. So you can regard the thread as like an execution unit that reuses all the process memory and has a region for itself to use a stack. Right, this is a complex question. From what I've read, one of the threads will handle the signal. It's not very clear which one. It's not a topic that I will cover in this thing. It's a little more advanced that I can afford right now for a second semester. But you can definitely find the answer in the manual actually. If you try man, let's say kill, and you search here for thread. Now maybe I think main 7 signal will give you something about it. All right, so just read here and you'll figure out how it works. All right, we have Marine asking, can a thread access local variables on the stack of main, or can it only work? Well, if it has an address, it can access anything in memory. I mean, look at this. This is the address of a variable local to main. And it's being accessed here. So yes, the answer is yes. You can access anything for which you have an address. Now, The issue, and I can come here and answer, let's see, the zombie threads question. At this point, there will be no zombie thread. There will be no zombie threads. Uh, all threads are part of the same process, and if the main thread ends, all the other threads end. So if you don't put a pthread join here, this will end when this ends, but there will be also undefined behaviors. And when I say undefined, I really mean undefined. I've seen really weird things happening if you don't put join. Anything can happen. I mean, anything that is possible in software. You know, the sun is not going to explode if you put a pthread join, but you may see really weird character printed in the console, although you have no printing going on in your program. So pthread join must be there. All right. So you use threads if you want to add two numbers at the same time, and process if you want to read to. Oh, William, I don't know how to answer this. Why would why would processes be better at reading than threads? Or why do you think that? For me, threads are lightweight. They don't use so much extra memory. Although even processes have been optimized massively, so it's not so bad. But one very easy to understand reason for using processes versus threads goes like this. Threads, you use little memory. You have implicit communications through shared memory, basically through the memory of the process. You have access to all of it. So communication is really easy. Creation is really easy. However, if you have a bug in a thread and the thread crashes, the whole process comes down. That's funny. Yeah. Um, two numbers at the same time. I don't, yeah, well, you might be one reading a number from somebody, another from another. I guess it's a legitimate question eventually, but why use processes versus threads? I don't see a benefit there. So I'll say this again. If you have a bug in a thread and the thread crashes, the whole process comes down. All the other threads dead. So then if you want to do computations and you want to make sure that the bug will not bring the whole thing down and leave some other things working, then you would rather go to processes. And this was a choice made by Chrome. If you start Chrome, you will notice that they have a process for each tab. And oh no, people don't write bugs. Nature writes them. People find them, right? So if you, I've heard a lot about Chrome being slow and being very large in memory, and that's possibly because they use a process for each tab. But because they wrote Chrome to be maybe more than a browser, you know, it's also part of the Chromebooks. It does a lot of stuff, not just browsing. They were probably concerned with stability, and they said, you know what? It's better to have a separate process for each tab, because if something fails in that tab, the rest will still be working. So they chose processes to make sure they have better stability. If you go to Firefox, I believe they use threads. If you go to Apache, which is a web server, I believe they use processes, multiple processes, and each process will have threads to serve requests. So you can do a lot of combinations. But this would be the easy part. You use process, more memory, a little slower creation, but if it fails, only that process fails. You use threads, easy communication, little memory, but if it fails, the whole thing goes down. So that would be some criteria for choosing one or another. So no zombie threads, although you can configure a, and here you go, you can configure a thread to be a daemon thread, in which case it will not stop when the main thread stops. And you would do that through these attributes. Yeah, I think they can. I never really tried it, but you know what? Why don't you write this and put a fork here and then you'll know. Just try it yourself. The worst that can happen is your computer freezes and you restart it and you're fine. Okay, so this was the story about what's a thread and what's a process, and how you choose one versus the other, and why we need join here. We really need join here. All right, let's move on to the next topic. So I'll open here the next way of passing arguments, which is with what if I need more than one argument to pass. Let me see what's Copsyman asking. If we use more threads than the cores available, will the program run? Okay, this is a complex question. So you are wondering, practically you're asking, will many threads help performance? How many threads will help performance? So you'll have to differentiate here between processor bound, IO bound, and mixed programs. If most of your program, most of your computation is purely processor, so just calculations, not a lot of disk and network communication, then usually a number of threads equal to your number of cores would kind of give you the best performance. But it's not a guarantee. It's just, let's say, a rule of thumb. If you have something that's heavily relying on I/O, then the number of threads that can help is defined by your I/O interface, how you're communicating with your I/O and how performant it is, how much it can multiplex. If your program is a mix, then usually much more threads than the number of cores will help. Now, yeah, if you want to go to GPU, then yeah, you have to go a little bit through the pain of programming the GPU, debugging it, and so on. But yeah, GPU will give you lots more threads. But what GPU does is mostly computation. That's not gonna do I/O for you much. All right. So let's get back to sending parameters. You guys jump really far ahead, but I still need to build this. So you're going to the top of the mountain. I'm still laying bricks on the foundation, but that's normal. So what if I want to pass to this thread more than one value? I'm just passing here an int. What if I want to pass several values? The only way to do that is to define a structure, populate it, and pass its address. So if you want to have a thread that takes more than one argument, put everything in a structure and pass it like that. All right. Moving on to parameter passing. Sometimes having a static parameter allocation is not that great of an idea, but you can always go dynamic. So instead of having 10 ints here, you can have a pointer to int, and you can allocate it just before creating the thread, give it the value of I, and pass it. And then here, do the same thing as before. The question is, where do you free this memory? The answer is when you don't need it anymore. And you don't need it anymore here. Now, many students, and unfortunately probably very few of those present right now, and many of those who are enjoying the good weather, will probably want to free here memory. But if you do free memory here, by the time the thread gets to access it, it will probably be freed already. So you'll get a memory error and everything crashes. So the way to do this is to free the memory in the thread. Basically, you allocate in one thread, you free in another. That's perfectly fine because both of them can access the same heap. Questions here, please, if there are any. After join, then you'd need to have an array of pointers because we're overwriting P here, right? You would have to have an array of pointers which you can free right here. But this is actually quite safe. Now I'm gonna make a parenthesis here. If you end up in a program, and this is happening for more complex programs, if you end up passing the same pointer to more than one thread, the question is which one of them will free it? The answer is the one that needs it last. But how do you know that? Okay, let's see. Why don't we allocate it before the for loop and free it after the join? But then we're in the same thing as here. You can, absolutely you can. But let's just think that what you're doing here is not allocating an int. You're actually reading from a socket data. And the socket tells you I have a message of 1,000 bytes, so you allocate here 1,000 bytes. And then you read the 1,000 bytes in here, and then you have to pass it. You cannot pre-allocate in this case because you have no idea how much you're going to read. This is the only place where you're going to read, you're going to know. So this is where you allocate it. Okay, let's see what else is going on here. You could put the pointer into a struct and count the ref. Yes, thank you, Rareshika. That's exactly it. The reference counted pointers in C++, smart pointers. I didn't know shared pointer is what they call it. Basically, that's what they do. So this reference counted pointers, the shared pointed counters, whenever you call delete on them, actually, whenever you pass them to a thread, because they use templates, they'll figure it out and increment the counter. And whenever you delete them, they decrement the counter. And only when that counter reaches 0, there will be an actual deletion of memory, releasing of memory. So this is the way you do it in C++, but in C you have none of that. In C, the only smart thing that you have is yourself. And sometimes even that fails. All right. But if you like pointer stuff in C++ and you are willing to get a headache, try this. So this is an awesome book if you really want to go into C++ stuff. I tried to read it. I didn't get to the end of it because I'm not using C++ so much. But it's a really dense book, and what this guy does with templates, it's actually scary. But you'll learn a lot. All right. Now, where are we going with this? Let's come back to the earth and put another brick. So, is everybody clear why we're freeing here and not anywhere else? Yep, cool. Good. Right, this example is, yeah, forget it. Now I'm gonna show you a dirty way of doing it. And it's really dirty, and it only works when you're passing an int. Only when you're passing an int. And you can use it if you're lazy. the compiler will complain. It's the only warning that we accept for the compiler. And it's basically a trick. Because an int and the pointer have the same size, if we want to pass I to the thread, we actually pass I, not its address, and we force it to be a pointer. And then in the function, we force that pointer to be an int. So this is actually working because the thread is not looking at the address of I, is looking at the value of I, which is passed forcibly as a pointer. When you compile this, you'll get a warning. My advice is to not use this very often, but it is functional as long as the pointer and the int have the same size. And you'll see me use this because it keeps the code a little smaller, and we can focus on the essence of that example. So these are the wordings that you're getting, but other than that, it will work just fine. All right, so this is the dirty way of passing parameters. All right, let's move on to the next trick, which will be a race condition. So let's see. Yeah, something like that. It's C. It's, it's just you and the computer. C is not really in between you at all. So up until now, we've talked about creating threads and passing parameters. But how about we do some concurrency work here? And I will start with the wrong thing, so that you understand the notion of race condition. So here it is: 10 threads, no parameters, but all these threads increment a global variable, and the main function, after the threads are done, prints out the final value. So the global variable starts at 0. We have 10 threads that increment this variable 1,000,000 times. So technically, the end result should be 10 million. In reality, it will be really whatever. So this is what we call a race condition. Yeah, but you don't have atomic in C++. In C, sorry. So I'm going to show you one way of making things atomic. You'll find it in many places. There are others, but so they are writing. It's not so much that they are writing as it's also that they are reading at the same time. So the explanation of this is really simple, and you've seen it already. N++ is actually a sequence of mov, bring the value in the registry, increment the registry, and move the value back. Now this is not necessarily accurate, but this is the idea of it, right? It's 3 operations, and then depending on how lucky you are, and this is also a matter of how crowded the work is, you may end up with an execution that looks like this for two separate threads. Right? So the first thread, the one on the left, would bring into the register, let's say 5. And this guy will also bring 5. This guy will increment to 6. This guy will increment to 6. They will both write back a 6. So we lost one increment. So with this, you can actually see this is happening quite frequently here. It happens about 8 million times, right? Because we get values of about 2 million. So we're losing 8 million increments because of this. N++ is not atomic. N++ actually is weird. Uh, because what I've just told you, N++ is not atomic. It's not real on all systems. It really depends. So last year, after I taught this class, I had my colleague Dan. Some of you might be doing seminar or lab with him. And he's coming up, he's like, look what I found. N++ is atomic nowadays. And I was like, no, it's not. Look, you have it right in front of you. And I showed him this example. He's like, well, this is not all right. Because I'm showing you the specs and they say N++ is atomic. And then we checked and it was all about, I was using GCC on Linux and he was using CLang on Mac, I believe. So depending on the compiler and operating system that you're using, N++ might end up being atomic because they might actually be translating it to a single assembly instruction. So some processors, some architectures may have a single assembly instruction for N++, whereas others may not. And then you may have a compiler that knows how to use that single instruction and others that do not. So until N++ becomes universally atomic, we will consider it not atomic. Yeah, I know. I know. I haven't gone so deep into the C compiler standards, but they are what they are. So N++ is not atomic. It can't be interrupted. You can get the operating system to even even if the operating system doesn't interrupt N++ after this the first column may be happening on one core and the second one on another, and you're done. So we need to make this be correct. And the question is, how can we make that correct? So before we go to the solution, let's clarify a few notions. This situation is called a race condition. A race condition is when multiple execution threads or processes access the same resource, which may be a variable, maybe a file, maybe a socket, I don't know, any of them, right? And so many of these access it, and at least one of them changes it. That's when you get the race condition. If many of them change it, then you can get wrong results. If only one of them changes it and the others make decisions based on the value, they might make decisions based on an incomplete value, a partial value. The write has not finished writing, but the read got whatever it found and made the decision on something that's inconsistent. So yeah, you guys are suggesting assembly. You can do that, but you can have this situation in Java, you can have it in C Sharp, you can have it in PHP, you can have it in Python, you can have it in any programming languages. And not all programming languages will give you the possibility of sticking assembly in there. And you're gonna hate anyway doing assembly C++. So no assembly here. The solution is to use synchronization mechanisms. And we are starting up with those. Yes, mutex it is indeed. We're going to start up with the first one. But wait, you're derailing me. Let's clarify the notions. So this is a race condition. In this case, n, the variable that it's, being contended by all these threads and processes, is called critical resource. And the piece of code that touches it is called critical section.